Okay, so this is mux. Okay, like I said, right, we'll be seeing mux a lot, and also we'll be seeing this. There's another building block decoder when we understand this memory system. Okay, so what exactly is a decoder? This is another building block. What we usually, when we say decoder, we usually refer to binary decoder. Okay, so this is where we have n inputs and to the n number outputs. Okay, so far most of the Boolean function we have seen, so where we actually have more inputs, right? We usually have more inputs than the outputs, right? And this is actually the other case for decoder. We actually have a lot more outputs. Okay, we just have a few inputs, and this function or this building block will produce many outputs. Okay, but actually producing the output in a very unique pattern. Okay, actually, this is something called a one-hot pattern. Right, so given any input combination, at most one of the output will be a one. So this is what we do with the decoder. Right, so let's try to be more concrete. Right, so by looking at a very concrete case, right, this is the simplest kind of a decoder, a 1 to 2 decoder. Right, so I have one input, right? So 1-bit input A, okay. And we have 2 to the n, right? So we have 2 outputs. So one's called Y1, the other one's Y0. So think of this as 2 lines, okay? 2 lines, output lines. And with this decoder, given an input, at most, one of the output lines will be hot or asserted or 1. That's why we call this a one-hot, right, decoding in this case. Okay, so what we have here is, again, we label the outputs. Okay, we use some decimal index. Right? We label one of the input as Y0, and the other one is Y1. When the input is 0, okay, the corresponding line Y0 is asserted. Somehow okay. And when A is 1, right? When A is 1, in the corresponding output line, Y1 is asserted. That's it. Good. So what is Y1 in terms of the Boolean expression? It's very simple, right? In this case, just A, right? Y0, A0. Okay. It's very straightforward. Let me just write it down for you guys. Let's get Y. Okay. And then we can generalize from this, right? Then you got 2 inputs. We will have 4 outputs. Again, out of these 4 output lines, at most one of them, right, will be a 1. Right. So we have 4 outputs. Right. Well, again, we label each output using this decimal index, right, from Y0 to Y3. So when A is 1, 1 over here, so 1, 1 means a 3, right? Y3 is hot for 1, and the rest of the lines are zeros. And you see this pattern, right? This is 1 hot. And this is the corresponding Boolean expression, right? What are these terms? In terms of A, it's based on minterms, right? But indeed, we have exponential number of minterms, right? So for 2 input, we have 4 minterms, and this directly corresponds to these output lines. And this is how the circuit diagram looks like, right? For 2 to 4, it's very simple, and we can further generalize this, right, to 4 input, right? For 3 input, 4 input. For 4 input, we will have 4 to 16, right? We just thought 1 to 2, right? 2 to 4, right? We can have 3 to 8, and then this is 4 to 16. And we have 16 outputs, right? Each output line basically corresponds to one of the minterms, right? So we already discussed the property of the minterms before in the second lecture, I believe, right? So where, given any input combination, right, exactly one of the minterms will be a 1, right? So same property holds here. So with this, we can actually also use this to build Boolean functions, right? Similar to mux, right? We can also, if we already have decoder, right, as one of the building blocks, it's already, something that we have implemented, we can use it to construct some meaningful Boolean functions as well. So let's just see how we do it. And this is a 4 to 16, right, decoder, right? We already have these minterms. So, hopefully this is already pretty straightforward. All we need to do is to put these minterms together, right? So for example, for F1, okay, so F1 over here, we just have to add one more OR gate, right? So this is F1, this is the OR gate, right? And this OR gate will connect to the corresponding minterms in this diagram. That's it, right? And we can, of course, use other minterms, right, to form other functions. For example, F2 and F3, right? I'm not gonna spend too much time over here. Hopefully this is intuitive enough, right? Since you guys are already familiar with some minterms. So with minterms, we can do all sorts of things, right? We can do sum of product, right? That's how we use the decoder, right, to implement logic functions. But actually decoder is more useful. So in the memory systems, that's something that we are going to discuss later on. Right, so this decoder. And there's also something, there's a variation for decoder. There's something called decoder with enable. This slide is more interesting actually, right? So with this enable, right? So, over here we have one more input to the decoder. So over here, this enable signal basically says that if this E, right, enable is a 0, okay, if E is 0, so all the output lines will be 0. So basically the whole decoder is disabled, right? So only when E is a 1, okay, we enable the function of the decoder. Does that make sense? Right. So that's basically where we add another signal. Okay, again, this is going to be more clear, right? So when we use enable, when we not use enable, right, later on. But for now, let's just try to understand the concept. Okay, in this case, if E is 0, it's will shut down the whole thing, right? Regardless of A1 and A0, so all Y's will be 0. Okay, so this is actually how we write the truth table. So this is more interesting, right? Let's just focus on this row. So see, there's some X, right, in the input columns, right? X also means a don't care in this case. So what this does is, so with this X, right, so we have something called don't care input. Really what we are doing is we are using a single line to represent many different combinations, right? So with 0xx, okay, 0xx means that we really don't care about, right, the value of A1 and A0. So with 0xx actually cover these 4 combinations. So what matter is in this row, right? What matter is E. When E is 0, all the outputs, right? All the outputs are 0. We don't really care about A1, A0. That's where we put don't care, right, in the input column. And again, this don't care is just like this so-called, in case you know the program is called wildcard, right? You can just replace 0, 0, or 1, right? And this basically covers 4 combinations for a single row. Does it make sense? Right. This is a decoder with enable. And this is how the circuit diagram looks like. Right. And the corresponding Boolean expression. Right. So see here, you look at the circuit diagram, we are basically adding this line, right? The enable line. So when E is 0, so since this is AND gate, right? So we have AND gate over here on the output side, when E is 0, everything will be 0. Okay. Otherwise, we have a normal decoder. Okay, so this is decoder, right? And decoder without enable and decoder with enable. Let me introduce one more thing, okay, before we end this lecture. We also have something called encoder. Encoder is basically the opposite of decoders, right? So with decoders, Decoder basically do sort of decompression, right? So we have we have fewer inputs, less inputs, fewer inputs than outputs. And with encoder, we have many inputs and few outputs. It's actually exactly the opposite, right? Encoder is like doing some kind of compression. You can think of it that way. So what exactly is a binary encoder? So over here we have 2 to the n number of inputs, and we produce n output bits. Right. Again, things will be somewhat abstract, right? Later on, this building block will be used, right? So that's where it'll be more clear, right? How useful these things are. Right. Some of you are asking, is Mux encoder in border term? Yes, you can say that, indeed for Mux, very good question, Lauren. So, we have fewer output, right, than inputs, but in this class, right, so let's define this encoder in a specific way, right? So let's distinguish it from Mux, right? So here's the definition of the encoder. So we have 4 to 2 encoder, right? So over here, what we have is we have 4 inputs, right? So I0, I1, or I0, I1, I2, I3, and 2 outputs. So what's the pattern here? The pattern here is that actually exactly only one of the inputs, actually, very, again, opposite to the decoder. So for encoder, exactly one input is asserted. It's exactly one input line is hot at any given time, right? You can see the pattern here, right? When I0 is hot, okay, the corresponding Y0 and Y1, okay, if this is 1, okay, the corresponding Y1 and Y0 is 0, 0, which translates to 0, right? When I1 is hot, right, over here, I1 is hot, right, Y1 and Y0, the corresponding output is 0, 1. So this is basically 1. Okay, is it clear enough? Right. And I2, right, over here, corresponding Y will be 1, 0. So which is 2. Okay, this is base 0, and this is basically 3. All right. Exactly the opposite to the decoder. Okay. This is a 4 to 2 encoder, right? So we just saw 2 to 4 decoder, and this is the opposite, 4 to 2 encoder. And this is a circuit diagram. Let me clear this a bit. So I'm going to ask you a question. So if you look at this circuit diagram, so how come like I0 is not even in there? Any ideas? Right? We have 4 inputs, right? I0, I1, I2, I3. Right. So when I0 is 1, it's a 0. I0 is a 1, it's a 0. Right. I think many of you are close, right? Close enough. So this means actually there must be some optimization going on, right? So this is the final circuit diagram, right? I can show you, maybe I can talk about this in the next lecture. I can show you how exactly this is derived. But let's first try to understand what's going on, right, at a high level. So is this a complete truth table? No, right? We have 4 inputs. So how many input rows, right? How many rows do we expect in this truth table? 16. How many do we have? 4. Okay, what's going on? What's going on with the rest of the truth table? Yes, so don't cares, right? Very good, David, right? And Ambrose, very good, right? So those are don't cares, right? I'll leave it here in this lecture, right? So basically, we are doing some additional optimizations, right? Because we have a whole bunch of don't cares. Okay? So that's why we are able to get rid of I0, right, from the circuit. Okay, so let me just spend one more minute, okay, to talk about another concept called priority encoder. Okay, this is very similar to the 42 encoder, but the only difference is, right, so we actually associate some priority on the input side. Okay, so in this specific case, okay, I3, okay, has higher priority, has highest priority, and the next one is I2, right? Because I3 has higher priority than I2, I2 has higher priority than I1, and then I0. And if you look at the truth table, okay, the priority is reflected like this. When I3 is a 1, okay, regardless, we have input don't cares here, right? Regardless of the other inputs, we don't care. So the output is going to be a 3. You're going to say, basically, line 3, input line 3 is hot. Okay, that's what the output is going to say. And if I3 is 0 and I2 is 1, again, regardless of the lower priority inputs, so we're going to generate a 2. Okay, so that's a priority encoder. And this thing, and this is the corresponding put expression. Right, so you guys can also try to derive the truth table and the kernel map to try to minimize it. And this is actually used in something called interrupt. And this is going to be covered in one of the later lectures. This is a priority encoder. That's pretty useful when we try to decode some of the external events, for example, power failure or like a keyboard, right? So when I press the keyboard or click the mouse, those are external events. Okay, all right, so these are the key building blocks, right? So we will try to make use of them, right, in a later lecture. Okay, let's end it here. I'll see you guys on